Hey, what's up guys, and welcome back to the channel. This video is a follow-up to the previous tutorial on animating a Mandelbulb in Maya with Arnold procedurals. I recommend checking that out if you haven't already, since I won't be explaining everything again here. So with the example procedural we used last time, we were able to use a PyMel script to animate certain parameters of the Mandelbulb, but besides the power, there really wasn't very much you could do with it. So I took a look at the source code, added more functionality, and compiled my own DLL. With the modified procedural, there are other formulas you can choose from, plus offsets, phase shifting, and more. I'm going to briefly explain the steps involved to add a phase shift parameter and compile our own custom procedural using the example as a starting point. We will also modify the PyMel script for adding custom attributes to the stand-in object, and the script for generating the sequence of Arnold scene source AS files. So it's going to help if you have some programming experience, but don't worry if you don't. I will try my best to make this as simple as possible. But if you're only interested in playing around with my example, feel free to grab the two PyMel scripts and my compiled DLL and follow the same instructions as in the previous tutorial. Some important notes before we begin. The version of Arnold for Maya needs to be at least Arnold Core 6.0.1 in order to work. If you are using the version that came with the initial release of Maya 2020, then you'll need to update Arnold. Some other things, this tutorial is for Windows and you need an IDE for C++. I'm using Visual Studio 2019. We also require the Arnold SDK along with the scripts included on my Google Drive. Both of these are available in the link in the description. And finally, and this is very important, on arnoldrenderer.com, there are two tutorials, and the example Arnold scene source AS file that we used last time will not work with the source code that they provide. So make sure you are using the files in the example folder on my Google Drive or on the site that we're about to look at, not the files that we used last time. So more on that later. For now, let's just get started downloading what we need. Okay, so throughout this tutorial, I'm going to be referencing the large datasets from procedurals. This is where I got the source code from, as you can see here, and the example AS file that we need is going to be underneath this section. And this is what differs on the previous tutorial that we looked at. So they do provide a different file here, and the variable names are different, so this is why it's not going to work. Now, you can copy and paste those files into your own, or you can go to my Google Drive and go to the starting files folder and download these files. So just make sure that you're using these and not the ones that we used in the previous tutorial. We also need the Arnold SDK. I'm using Windows, so I'm going to download this for Windows. Now, you do have to log in with your Autodesk credentials. If you don't have an account, you need to make one, then you agree to the terms and download. So I already have a project folder created for Maya, and inside the project folder, I'm including the Arnold SDK. You really should put this somewhere else, not in your project folder, but I already have this installed where I need it, and this is just for this tutorial. So this can go anywhere on your computer, but you would probably want to put it in your C drive or something. I also have those starting files, which is an example Arnold scene source file, the source code, and the two Python scripts. I also have the scene that we used last time. You can download that here. And of course, if you'd like to use my full versions of the Python script, the source code, and the DLL, these are available to download as well. For the first part of this tutorial though, we're just going to use these starting files so we can do something pretty simple, and then later on we'll have a look at these. Okay, so the first thing that we need to do is take a look at the source code. And to do that, I'm going to use Visual Studio. So I'm going to create a new project. I'm going to use a desktop wizard to do this. For the project name, just call it Mandelbulb, and in the location, I'm going to create a folder called Visual Studio. And I'm placing the solution and the project in the same directory. So click Create. The type of application here is going to be a dynamic link library or DLL, and we're using an empty project. So this just creates a bare bones DLL project for us in Visual Studio. So the first thing that we need to do is then load in that CPP file. And there are two ways you could do this. You could go in and add a new item and then just copy and paste the source code from the website. But if you've downloaded the CPP file, we can just add that as an existing item. So we'll do that, go into starting files, and then we'll just load in the Mandelbulb CPP, and then double click this file. So as soon as you open up the CPP, you'll notice that several lines are underlined in red. This is because it's referencing objects and functions in the Arnold SDK. So we need to configure our project so it uses the SDK. To do that, you can just right click over the project name, go to properties, and we need to go into the configuration manager. And this is very important to change this to x64. This is a 64-bit application, and we need to change the solution to release and then close. Next, under C++, in the additional include directories, click the drop down arrow, go to edit, and then we're going to add in a new line here. Navigate to the Arnold SDK include folder, copy this path, and paste it in. Next, under linker, go to input, and then we need to add an additional dependency. Go to edit, then navigate to the Arnold library folder, and we're going to copy this path here, and then manually type in ai.lib for that library file. Then click OK. Then click OK again, and now all of the underlines should be gone because now it is linked with the SDK. So the first thing that we need to do is make sure that we can compile this into a DLL. To do that, go up to Build, Build Solution, or you can just do F7. And this is going to fail. And the reason it's going to fail is because there's an unsafe string copy function here. This is pretty old. So we need to use a safe version of that. So you can do _s. If you want to force it to compile, you can do so. You can look up where you place this code here. Otherwise, just use the safe string copy and everything will be good. So let's click F7 again. You can see that it's successfully built, and then we need to go and find where that is. So by default, that is going to be under your folder name. So mine's called Visual Studio, project name, x64 release, and it's going to be this right here. We're going to take this DLL and we're going to paste it in the root directory. Now, every time we compile, it's going to compile to the folder that we just looked at. But if you try to compile while Arnold is using the DLL, you won't be able to. So it's a little bit annoying, but every time that you want to compile it, just copy and paste it out of the folder, and then you won't run into issues. So let's take a quick look at how the code works and how it relates to the Arnold scene source file. So let's go into the starting files folder and have a look at the example AS file that they provide on their website. So if you recall from the previous tutorial, we don't really care about any of these settings here. So this is creating things like a light and a ground plane and some materials. We don't really want any of that. So we're going to delete that. And we're also going to delete this shader line as well. So I can go ahead and save over this. I don't really need anything else. And this is the part that is really important to make sure you understand if you want to add your own custom parameters. When Arnold loads the DLL, it passes the data in this file through the DLL to then create the Mandelbulb. So these settings here are our way of interfacing with the DLL to pass custom settings. So if I wanted to change the size of the grid, or if I wanted to change the power level. Now these are the only things that we can do currently, but what we're going to do next is add our own custom attribute to alter the phase. And you'll see what that does a little bit later. If we take a quick look here at the code, at the very beginning, we have a struct. This is a data structure that contains the variables listed in the AS file along with a counter, which is not very important for what we need. And if we scroll down here, this section is what is reading in the AS file. So here it's looking for specific variables, grid size, max iterations, power, and so on. And these names need to correspond exactly with the names in the AS files. If you use the previous example on their how to render a Mandelbulb tutorial, the AS file that they provide has different variable names. And if you change the name, so for example, in that previous one, it was grid size. If you try to load this in, it will not be able to generate the Mandelbulb and it will give you an error because it doesn't know what this variable is. So just bear that in mind that whatever is listed inside the source code needs to match what is generated in the AS file exactly. Okay, so a very, very brief description of how this is working. You pass in parameters from the AS file, and for every cell of the grid, and the grid is a 3x3, so X, Y, Z coordinate grid of points. For every point, it runs the iterate function, and that iterate function uses the formula for the Mandelbulb to figure out where that point should be in space. The equation is derived from the Mandelbrot equation. If you're interested in the equation, check out this Wikipedia page, which goes in a little bit more depth of how this is created. And there's other resources out there online that are a lot more in depth. This is basically the equation that is being converted into C++ and what is used for generating the Mandelbulb shape. So in my example, I also added some non-trigonometric functions to do the quadratic, cubic, and quintic Mandelbulbs. And there's other ones too. There's power 9 and spherical ones. And then there's dozens and dozens of derivatives of these. So if you're interested, there are resources available elsewhere, but for this, we're just going to continue to use their standard Mandelbulb. Now, this code is also very inefficient because based on your grid size, it has to run this iterate function thousands and thousands or millions of times, depending on how many cells you have. So they do mention that you could use single instruction, multiple data functions. So we're not going to be doing any of that. This also would be probably greatly improved by passing a lot of this data to the GPU to calculate because it can do it much faster than the CPU. Now this code is multi-threaded, so if you scroll down to the bottom, you can see some functions that are set up to handle different threads and chunk sizes. The number of threads is also available in the AS file, so you can increase your number of threads here if you'd like to. So unfortunately, this is a very inefficient way of doing this. Also, keep in mind that this is generating a cloud of points, essentially. So it's not just the surface that we're generating, we're also calculating and generating what is inside that shape. So I'm sure that there are far more efficient ways to do this. We're not really going to look at that. We're just going to keep what they have done and then just add on some functionality. So the point of this is to experiment with procedurals, and that is the main goal. And this code is just a tool in order to do that. So we could go ahead and make it way more efficient, but that is not the point of the tutorial. So what we need to do now is modify our first Python script in order to add some attributes in Maya. And to do that, we're going to have a look at this add attributes script here. So if we load this into Visual Studio, you can load this into any text editor as well, or a specific IDE setup for Python. So this is the same script that we used last time, but we want to add a phase shift. So I'm going to expand this out, zoom in a little bit here, and this is what is adding attributes to the Maya file. So I'm just going to enter down once, and then we're going to add a line to add an additional attribute to the extra attributes tab. The name of the attribute is going to be called phase. Keyable means whether or not you can animate it. The type is going to be a float, and the default value is just going to be set to 0. So after we have this, then we can simply save this file, and then we can load this into Maya just to make sure that everything works. You can grab this file in the link in the description as well if you just want a quick starting point. I already have the stand-in set up, but there's nothing loaded into it yet. Click on the AI stand-in, open up your extra attributes. Now these attributes are already default when you create a stand-in, so we want to add some more to these. So in the script editor, I'm going to open up the Mandelbulb add attributes script. Zoom in on this. So this is what we just changed in Visual Studio, added that phase. Now to run the script, you can click the numpad enter key or you can click execute. And then if we scroll down here in your extra attributes, you can see that the phase has now been added. So that is how you can add some extra attributes. Okay, so let's go back into Visual Studio now. And next we need to modify the Mandelbulb animate script. I'm going to drag this one over. So what this script is doing, it's taking all of these attributes here and then writing them to an AS file. So it's going to generate a file like this. So we're going to scroll down here and then right underneath Julia C, we're going to add in a variable for that phase. All right, so for this, I'm going to use the same variable name just because I find it makes more sense. If you like a different convention, that is perfectly fine. We just call pymel.getAttribute shape, and then we get the same attribute name as what we just created. So this corresponds to what the name of the attribute is in the add attributes script. And this is set up so every frame generates a unique AS file. So this is what the time is for. So this variable is storing whatever we do in Maya. So if we animate this for every frame, a different value will be stored in phase, and for all of these other variables too. So then we need to write this to the file. So we're going to come to the end here, and then we're going to cast this as a string and then add a new line. And that is all we have to do here. So next we need to load this script into Maya and just check that it works. So once again, just go to File Open, Mandelbulb Animate. Now, if you recall from the previous one, we do have to set up a custom location. In your set project, you should go ahead and then make a folder for your AS sequences. Then we're going to copy this path and paste it here, and we're going to add double backslashes. I know that this is kind of irritating and I never made this script work without having to do this because I am lazy. So just go ahead and make sure you add either a forward slash or use the double backslashes. So once that is set, we should be good to go. And you can see that phase is being added here. Let's go ahead and animate the phase. So at the very beginning at frame 1, I'm going to set a key, and then by frame 120, we can do something like 1. So between 1 and 120, this will go from 0 to 1. You could use whatever number you want here. It doesn't have to be an integer. It could be a decimal point as well. I'll also set my grid size to be 400 because this is the number one thing that causes your renders to be really slow. Just keep this variable low while you're just playing around with it. So let's go ahead and then export out this AS sequence. So to do that, we're going to make sure our AI stand-in is selected and then run the script. So remember that these variables here don't actually do anything until we first run the script and then load in that sequence that the script generates. So here we're going to go up to open, AS sequences, then load in this one, then use file sequence. All right, so now let's go ahead and then look at this sequence. And you can see that right at the very beginning, the phase is at 0. And as we go further on, let's just arbitrarily go to frame 90. You can see that the phase is increasing. So what we've done, we've added the attribute now, but right now, this doesn't mean anything to the DLL. So we need to create a parameter inside the source code that can actually take this variable and do something with it. So back in the Mandelbulb CPP file, we need to go all the way up to the top. And the first thing is inside the struct, we need to define a new variable. So we're going to define a new float, and I'm just going to call this phase. It applies a phase shift. And then we're going to go down to the Arnold parameters and add in a parameter for it. This is a float. If you're adding a different parameter, just make sure that you type it in correctly. So there's ints, floats, but not all of them are spelled out. So just bear that in mind. And a vector is a specific Arnold vector. It is not like a dynamic array vector. Just bear that in mind as well. Now this name here needs to match what is in the AS file. We call this phase, so we need to write in phase. Then we're going to just go ahead and add in a default value of 0. Just line that back up. Now, in order to assign whatever is in the AS file to the variable we defined in the struct, we're going to do that here. So we're going to assign the bulb phase parameter to the number that is assigned to phase in the AS file. So if we're on frame 44, for example, it's going to look at the number that comes after phase right here. So this is very important. If you had something like phase shift, this is not going to work because it's not the same name. So to make sure that this matches exactly. All right, so right now we still haven't done anything with this. We're able to pull that variable in and store it inside the structure. But in order for it to actually do something, we need to add it to the function. So we have a function here called iterate, and this is what is generating the Mandelbulb shape. And this is where we would want to add the phase shifting. So we're going to modify this iterate function. So to do that, we need to pass in an extra argument. So we're going to do float phase. I understand that a lot of people don't like to use the same names for variables and function arguments. I know that they are different, but I prefer it to be the same name. So you want to change something to like an underscore and then use phase up here. Just keep in mind that these two are different variables, but they will pass in the same information. This is not really a coding lecture, but I kind of know that a lot of people don't like that, but I do. Right, so the way that we add the phase is in the theta parameter. So we just add the phase here. I'm not really going to get into the math of this. This is where you would place this for it to kind of ripple. That's essentially what the phase is going to do. Okay, so you will have noticed that there's two little red dots down here, and that is because we've added an argument, but then this function now can't work because it doesn't have that fourth argument. So we need to add that in. And we can just copy and paste this here. So we have now added the functionality to be able to change the phase. All right, so we can now go ahead and compile this. So we can click F7 to compile. So that's succeeded. Let's go back to our Visual Studio folder and navigate to where that's saved. Mandelbulb DLL here. I'm gonna copy this, then I'm gonna paste this in the root, and then we can go back into Maya. So inside our render settings, under system, we do need to add in the plugin search path. So to do that, we're just going to go to the project name, paste in this path, and then type in mandelbulb.dll. So this is what is installing the plugin for this scene. Now in the previous tutorial, recall that there are two other ways that you can do it. So it will be accessible from any Maya file, but if you haven't set up that in your Maya environments or in the Arnold plugin path, you can just do it here, which I prefer. And now we can click render. All right, so there's our Mandelbulb. Now, if we go forward, and if we stop the IPR and then go halfway, we can take a screenshot of this, then update the scene again at frame 60, and you can see that the shape is different. So we are getting that phase shift. we compare these, you can see that they're different. So let's go ahead and render out a full sequence of this so we can really see what it's done. So we're going to switch our tab to rendering, go into the render settings here. I'm using the GPU, going to enable some adaptive sampling. And then in the file name, we're just going to use that scene token again. And then I'm going to use an underscore. It's going to be phase/scene phase. I'm going to render this at 4K UHD, basically the same settings as we did last time. So in AOVs, I also have a depth pass, and then under the driver, I have it selected so we're merging the AOVs into one EXR file. And you can confirm that this is set by going to common merged AOVs. Just make sure that that is set. This will give you one EXR with all your passes, which is generally how you composite things. Also in diagnostics, the verbosity level for the log is a debug. This is very useful if you run into an issue where there's something unexpected that happens and you want to go back and look, or maybe a frame failed and you want to see why it failed. All right, so then with that all set, you can go ahead and render this. We'll go to render sequence. So this is something that we couldn't get before. In order to get it to move, we had to change the power level, but changing the power of the equation changes the shape, like dramatically sometimes. So if you want to maintain the same shape, but you just want it to kind of ripple back and forth, you can do so pretty easily with the phase shift. So I hope that kind of makes sense of how you can begin to add in controls. Now, what if you wanted to add in a completely new formula? So for that, make sure you have downloaded the files with the CGStirk suffix at the end. So I'm going to create a new folder here just called Mandelbulb_CGStirk and just paste these files in here. So I'm going to close these tabs up here, and then I'm going to go ahead and add in my version. So I can exclude this file from the project now, and now we are just looking at my version. So as you can see here, there's quite a few new variables. The very first one here is this offset XYZ. And what this does, it simply adds another number to the X, Y, and Z position. So you could do something like have the shape start off from the side and then animate inwards. So this does change the shape of the object, but it gives some really interesting results. So check out the end for an example of this. And this is added to the standard Mandelbulb, which I did change the name of these functions. So instead of iterate, this is now iterate Mandelbulb. Then we have iterate cubic and quadratic and so on, which leads into the other formulas that are now included. So if you recall on the Wikipedia page, there are some non-trigonometric functions for the quadratic, cubic, and quintic Mandelbulbs. So I simply implemented these functions in the source code. You can see here, it's not the cleanest way of writing these equations. They're a little bit clunky with the power float functions, but it gets the job done. Also on the quintic formula, there are 4 coefficients that are added. So you can change the shape dramatically by playing around with these numbers. All of these are controllable in Maya. Scrolling back up to the top here, I've also added an option to make sure that this is a standard Mandelbulb. So because in Maya, you could technically check several different formulas, there has to be a check to make sure that you've only checked one of them. Otherwise, it wouldn't really know which one to do. There's also an approximation that you can use for the standard Mandelbulb. So if you recall in the previous source code, there was a clause that says if the power equals 8, then it's going to use an abbreviated formula, which is more of an estimation. But this gives a pretty interesting looking result. So I have that now as an option that you can estimate the Mandelbulb, which gives more of a cloudy-like appearance, more a loose appearance rather than a very tight object. So you can play around with this setting. As I said, there are going to be examples of all of these at the end. Then we have some Boolean operations, which switch the formula based on what is checked in Maya. And then of course those quintic coefficients. But one of the most interesting things about this is that there is also the option to combine any one of these other formulas with the standard Mandelbulb. So you can have the quintic shape kind of merged in with the standard Mandelbulb, which gives very, very interesting results. Some limitations of what I've done so far is the phase only works on the standard Mandelbulb. I didn't go ahead and implement that for the other ones. And if you're using the standard Mandelbulb and you have the Julia option checked, it only applies to the standard Mandelbulb. This can get very complicated very quickly. So if you wanted to have Julia combined with the cubic, quadratic, and quintic, you would have to come down and change the source code. So where it actually checks to see which one is selected is in the fill list function. So I modified this one, so it is going to ask whether or not the is cubic is checked, and if it is, if Julia is checked and it is not a standard Mandelbulb, it does the Julia function. We haven't really looked at Julia in this series, but it's more of a cloudy-like appearance instead of a more solid-looking object. Otherwise, it just does the regular Mandelbrot version of that. And at the very end, it's checking to see if you want to combine that with the Mandelbulb, and if it does, it runs through another iteration for the standard Mandelbulb. Now, this is extremely inefficient code, like I noted before, but it does give some really interesting results, especially if you are wanting something that's a little bit more, that looks more like a bunch of particles, because this is just a bunch of spheres. So let's go into Maya and then take a look at the Python scripts. So inside Maya, we need to close these two tabs for the original Python scripts, and then we're going to go in and load in my versions. So switch the folder to Mandelbulb CG-Stirk, and then we're going to do the add attributes CG-Stirk, and then the animate CG-Stirk. All right, so for the AI stand-in, it's easier just to delete the stand-in and then make another one. So to add a new one, just go up to Arnold, stand-in, and then make sure that is selected in the outliner, and then you can run the add attribute script. And you can scroll down and you can see there's quite a few more variables added. Now, one limitation with how this is set up in Maya, and I don't really know if there's a way around this, you could technically choose to use a cubic and a quadratic formula. And if you try to run the script, it will give you a warning that you can only choose one. So this is a check that is done both in the animate script. So if we go down to the bottom here, it does check that only one is selected and it will give you an error message. Now, of course, you could go in and change the AS file manually, but there's also a check in the C++ DLL. So if we scroll down here, there's also a check. All right. And if more than one is selected, it will just return nothing. I'm sure there are better ways to check this, but that's just what I came up with as a quick workaround for that. Now, any one of these parameters here is animatable, and some really cool ones to play around with are the quintic formulas. So you can play around with the quintic ones. You can also combine this with the original. Now, just remember that if you want to use any one of these, you do have to uncheck the standard Mandelbulb. You can also, of course, approximate these and then play around with the original settings that we had as well. This still could have a lot more functionality. So if you're interested in expanding upon this, feel free to use the source code and make it a lot better and add other functionality. Sometimes I do lose interest quite quickly, and if I don't get a tutorial out on something soon enough, I kind of go on to other things. So kind of stopped at this point, but there's so many different types of formulas that you could use and derivatives of other formulas. There's some really cool software called Mandelbulber and Mandelbulb 3D, and those are really, really cool pieces of software. Now, the limitation of those is you can't really do very much outside of those applications. So the reason I started this is because I was trying to do something in Maya, and this was a solution to play around with some interesting abstract fractal shapes. So if you want to go ahead and make this a lot better, I would love to see what the end result is. So don't forget, you actually have to load in the new DLL. So in the Arnold render settings under system, this is still path to the original one. So we do need to take in the path of the new version here. So let's say I wanted to play around with a quintic one that was combined with the original, and I want to approximate it, and I want to play around with the power or something. So all of these are the same types of settings. So just make sure this is going to where you want it to go. In this case, I could make a new folder specifically for my versions of the AS sequences. So we can just tack on CG-Stirk to that, and then on the file name too. And then go ahead and run the script. And then you just load it as you would with the other one. All right, so let's do a little test render. So this is an example of something you can get with the quintic formula. Now here are a bunch of other examples that I played around with using my version of the DLL. So there's endless possibilities of what you can do with these shapes, especially if you go into the source code and add more functionality. I hope this sheds some light on how you can create your own custom procedurals with Arnold. So if you learned something, a like really helps out the channel. I also have a Discord server now, so if you run into issues and you're trying to follow along, you can ping me there and attach screenshots and stuff, so check that out if you're interested. Alright guys, thank you so much for watching. See you next time. Peace.